So, up to now we have only calculated for only one state, and that is one route. Now, question is that if I want to calculate more than one state, because CASSCF, remember, like a CI, it can not only give access to your ground state, it can also give you access to your excited state. And when you need to calculate the excited state, remember you have to choose the orbital space in such a way that it correctly represents that kind of excitation energy. So, we are going to again use the example of formaldehyde, and because we have already done calculation on formaldehyde using chem-B3lib, this is how the orbitals will look like. And this was the singlet and these are the for the triplet, and this was what we got for the excited states, and how this is how the orbitals looked like. Now, you can see that for the second excited state and the third excited state, it actually have considerable Rydberg character. One of the problem with MP2 natural orbital is that it generally throws away the Rydberg orbital towards the end. So, it does not, the Rydberg orbital does not come near the valence space, not near HOMO, LUMO. So, the Rydberg orbital does not come near the valence space, not near HOMO, LUMO plus 1, LUMO plus 2. Because these orbitals are very diffused, they generally have very negligible contribution to the ground state energy. So, NP2 natural orbital orders the orbital with respect to their importance in the ground state energy. So, if I use MP2 natural orbital, this kind of orbitals will not be selected in the active space. So, good idea will be to, in these cases, is to do TDDFT calculations and see which orbitals are important for that particular kind of transition, and then take them in the active space. And for the H2CO, we have already done this calculation where my excitations were dominated by excitation from HOMO minus 1, and these are from LUMO plus 1, LUMO plus 2, LUMO plus 3. This is where the orbitals I need to take care in the calculation. So, the first step of doing CASSCF calculation for the excited state is to do this TDFT calculation and see what kind of excited states are necessary. Remember, this trick is only going to work if you are interested in the excited state dominated by single excitation. If you are interested in the excited state which are not dominated by single excitation, you want to go to double excitation, for that kind of state it may be problematic and these tricks will not work. So, for that you need to do initial CASSCF calculation, see which orbitals are important, and then take that orbital to actually do the proper CAS. So, let us first do the CASSCF calculation. I can already use my existing orbital input file and bring it here. I no longer need this TDFT thing. Because I just need to start with the initial orbital. Okay, I could have done the TDFT calculation just to be on the sure again. Anyway, it does not take a long time. At least for the first few root, you can see that this is dominated by HOMO to LUMO plus 1, this is also HOMO to LUMO plus 2, and this is HOMO to LUMO. So, basically for this orbitals generally it is sufficient to get you at the active space which is dominated from HOMO. So I can just take, just to be on the safer side, I can take two orbitals, HOMO HOMO minus 1, and in the virtual space I need to take all the dominant transition, that is LUMO, LUMO plus 1, and in this case it's LUMO plus 2, it's LUMO plus 3 actually, and this is your LUMO plus 2. So I at least need to take 2 active orbitals and 4 virtual, so 4 total 6 virtual orbitals and 2 electrons for doing the calculation. So 2 for these 2 occupied, 7, and just on the safer side I will take the 6 also in the active space, and for the virtual I have LUMO, LUMO plus 1, LUMO plus 3 and LUMO plus 2. So total 4 unoccupied and 6 occupied. Sorry, I have to take this HOMO, just to be on the safer side I will take HOMO minus 1, and on the virtual I will take LUMO, LUMO plus 1, LUMO plus 3, LUMO plus 2. So 4 virtual, 2 occupied, total 6 orbital active, and I have 2 electrons active. So this is how the input file will look like. I will discuss much more about the input file. So now I will read from H2CO KMB3 lib GBW file. Now question is that you can do actually calculation for both the multiplicities, both multiplicity 1 and multiplicity 3, and now if your molecule has symmetry, then it will calculate the roots by irreducible representation. So for both these symmetries, okay, number of roots I could have made 4 4. This n root is equal to 4 comma 4 will say that the first it will calculate 4 roots from the singlet multiplicity and 4 root from the triplet multiplicity. And for the for the symmetric molecule, for the molecule having symmetry, we need to use the irrep keyword, and this says that for multiplicity 1 I will calculate roots from 0th irreducible representation, ORCA start from 0, that means its first irreducible representation, that is A1, and for the triplet also I will calculate from A1. I could have do 2 different irrep for 2 different multiplicities also. So let me save it as H2CO gas SA. Now why I am writing SA? It's because I am calculating 4th root. Now the question is that orbitals are optimized for which one? So basically the orbitals will be at state average orbital, where orbitals will be average of all the 4 excited state roots. Generally the singlet and triplet averaging of orbitals generally happens separately. So different multiplicity blocks generally get averaged in a separate way. Let us see the output. These are finding the symmetries. So number of multiplicity block is 2. So for the triplet also it will generate the A1 configuration. For the singlet also it will generate the configuration A1. So these are the initial CI steps where it will give the initial roots. 8.60 is the initial CIS root and 9.986 is the initial CIS root. Now it will do the optimization. And you can see that the singlet and the triplet are getting converged in a separate way. So number 6 number of orbital is actually doubly occupied. So that may not be a good idea to take in the active space. Irrespective of that, we can see the values. So for the triplet, the root is 6.61, and for the singlet, the first root is 6.65. If you go back to the picture, these results are not as good as KMB3 DFT result was suggesting. So how one can improve that? So one can improve this kind of calculation, because remember what is happening in CASSCF. It's only considering the non-dynamic correlation. There is no dynamic correlation there. So to do the dynamic correlation, one need to include the effect of Y using either perturbation theory or CI. We are going to use the NEPPT2 for this kind of calculation, because that can include the dynamic correlation in a perturbative way. So the only thing I need to change in this block is NEPPT2 calculations are generally quite cheap, and you can always do it after a CASSCF calculation. So I will now again rerun the file. Now if I again reopen the file, see that the input file looks very similar as the previous. So first it will do the CASSCF step. So once it is done with the CASSCF step, it gives you the corresponding energies, and after that it will start doing the NEPPT2 calculation from here, and it will first transform the integral via Ri, and then for each multiplicity it will start doing the calculation. So this NEPPT2 calculation for each root will be done separately, root 1, root 2, root 3. So, actually NAPPT2 in this case does not really improve the result so much. So, you need to choose a better active space which can do the calculations for you. So, that means I have not chosen the active space very properly, and clue is in the this kind of an orbital. So, that means we have to improve the orbital space, and that can actually give me much better results.